We're going to talk about kinetic energy and the work energy theorem. And this is one of those, the work energy theorem sounds very scary. But it's one of these things it's a big idea in physics. So Gage will enjoy this. It's profound. This is profound. All right. So anyway, let's review a little bit. We have this idea of work. And we said that work is equal to, well, I'll just write it down like this. F dot delta R. Okay, it's a dot product. And of course, if the force varies with your position, you have to use integrals. So this is kind of the most basic definition. And this is a force times a little tiny displacement. And then you add them all up. You sum them all up and you get the total amount of work done. But what is work? Work is when you're transferring energy from one system into another system. And that energy is going to be manifested or it's going to be stored up in different ways. And I like to think of kinetic energy as a way of storing energy. Okay? You're storing it in the movement of some object that has mass. Okay? It's normally not thought of as a potential energy, but you are, potential energy means you're storing energy because of the position of an object, and we'll get to that later. But kinetic energy is when you store energy in the motion of an object. Okay, so let's transfer some energy into something. Here's a flat plane. And this is kind of the easiest way to derive this. Okay, here's a crate with wheels, and it has some mass. Okay. And let's say that it starts off with some initial velocity, and I'm going to push on it with some force here. And this force is going to do work. Now, this, what's doing the forcing here? Some object, some person pushing on it, or a rope that's pulling on it, or there's a jet engine here. I don't know. I don't care. But in any case, the agent that's applying this force has energy, has the capacity to change its environment. It's going to change this massive object, and it's going to give it more velocity. So let's say its initial velocity is kind of off to the right, and we push on it through some delta x. So here's the crate at delta x, and its final velocity is greater. Okay, and here's that force still acting on it. It's a constant force in this case. Well, let's give it wheels. It's not a hovercraft. Okay, and there we go. So we're going to look at this situation. So what I'm saying is that whatever is applying this force here is transferring energy into it, and is transferring that energy into the motion of this moving crate. Well, how much energy was transferred? Well, obviously we can figure out the work done. That's equal to this force times this displacement, and everything's all lined up here, so I can just use F times delta x. Okay, but here's something to consider. Look at this object. What is true about this force acting on the object? Well, if I draw a free body diagram of it, okay, yeah, sure, we've got gravity pulling it down, we've got a normal force supporting it, and this is the only other force acting. So therefore, this force right here is equal, or is the, what kind of force? It is the net force. Okay, and so that's going to be equal to the mass times the acceleration times delta x. Okay, now in this case, I am going to assume that that the force here is a constant force. Now in a few minutes I'm going to derive this with pure calculus, and then you don't have to make that assumption. But we can here. let's say the force is constant throughout time, doesn't vary with time or position. So we can use the kinematic equations here. And what I'm going to do is I'm going to use the kinematic equations to replace acceleration. And I don't really care about time, so I'm going to use the fourth kinematic equation where it says v squared equals v naught squared plus 2a delta x, right? This is an equation we can use when we have constant force, constant net force, and constant acceleration. Let's solve for the acceleration here. A is equal to v squared minus v naught squared over 2 delta x. See, what I want to do is I want to express this work done in terms of the velocity of the object, right? Because I'm transferring energy into it, and the result of transferring energy into it is to increase its velocity. So I want an expression for work transferred in terms of the velocity change. So that's why I'm using this this kinematic equation, because it has velocity in it. And it's also very convenient. You'll see, this is kind of like a little proof here, that when I make a substitution, something wonderful happens. I get mass, and then I've got acceleration, which is now v squared minus v naught squared over 2 delta x. But then I multiply by delta x, right? I'm up here. And what happens to delta x? It goes away. And now I've got an expression that's just what I want. The work done, that is the energy transferred into the object in terms of its mass and its motion. Now I'm going to rewrite this. And I've got the mass, I've got the final velocity squared over 2, and then minus this thing. So I'm going to say this is 1/2 the mass times the final velocity squared minus 1/2 the mass times the initial velocity squared. And this is really my end result here. This is what I wanted. Now, I could say this. Let's suppose that my initial velocity was 0. And so I applied this force to this displacement. And so I would get 1/2 mv squared, where v here is the final velocity squared. Well, I did work, which is a transfer of energy. A transfer of energy resulted in motion, a massive object that's moving. Now, you all know that a massive object that's moving can do work on stuff, okay? And again, if you don't believe me, go play on the freeway. And you will find that moving objects can do work, can make changes, radical changes, okay? So, and that's what we're looking for. So, this right here, the energy that an object has, because it's moving and has mass, is called kinetic energy. Okay, so, and we use, and we're going to use in this class, and it depends on what textbook you use and who your professor is or whatever, but in this class we're going to use the capital letter K to represent kinetic energy. Well, then this right here would be K final. The final kinetic energy of my moving crate up here. And then this would be the kinetic energy it started with, and I'll call that the initial kinetic energy. And of course, whenever you have a final minus initial, you can express that with a delta, right? So the work done by our net force will result in a change in kinetic energy. Okay, now this is a law of nature right here, and I'm gonna rewrite it here. Well, I'm gonna write it out in words. I'm gonna say this. the work done by a net force will be equal to the change in kinetic energy. So if you're doing work on an object, and you're looking at the work done by the net force on an object, the work done will be equal to the change in kinetic energy of that object. And this is called the work energy theorem. And it's kind of a big deal. It's kind of a big deal. It's not as big a deal as F equals ma, but it's a pretty big deal. I mean, all these laws all work together to explain the natural world. So, you know, it's all right. Now, I'm gonna derive it now. This derivation right here of the work energy theorem is the one that I use in regular physics. But this is AP physics, right? AP physics C. Okay, not AP physics B. Okay, that's a mile wide and an inch deep. This is AP physics C. Fewer topics, but we use calculus. Okay, we get into the. You're getting the real deal here. This is the physics that Newton invented. All right, and so what we can do here is go back to our most basic definition of work. Oops. That didn't help. Okay. Oh, I'm sorry. Thank you. Now we're going to say the work done by the net force, dr. Okay? So this is the work energy theorem. Now, this right here is equal to ma. It's still, you know, whenever you have the force, the net force, even if the net force is changing with time, at that particular time, it's going to be equal to ma. So this is going to be ma, and we're going to have a dot dr. Okay. Now let's punt a little bit. Let's get rid of this dot product thing. Let's just say everything's going to line up. Okay, we'll have the cosine of the angle between them. But let's let that just drop away. Keep everything in the x direction. This is going to be ma times dx. Well, what is this right here? Let's express this in terms of its differential equation. Mass times acceleration is what? It's dv dt times dx. The reason I switched to x is because that's the way the book's doing it. You're going to be reading the book. All right. Now these are just little tiny fractions, right? I mean, you think of a differential as being a little teensy-tiny little thing. Okay, but it's just a factor. I can rearrange this. And I'm going to call this dx dt. And then I'll put the dv out here. But what is dx dt? What is that? A little tiny change in position divided by a little tiny change in time. That's velocity. Oh, mass is a constant, so I'm going to bring it out of the integral. Now, v times dv. Well, this is the easiest integral in the world to do. I mean, it's just the power rule, right? What is v times v? V squared. But you got to divide it by the new exponent because the calculus gods tell me I have to. And we have to go from some initial velocity to some final velocity, right? This has got to be a definite integral. And so what I get is 1/2 m v squared going from v initial to v final. And so you get 1/2 m v final squared minus 1/2 m v initial squared, which is, of course, the work energy theorem derived with calculus. So let's look at everything here. Whoops, wrong way. So we now have, this is our first form of energy that we really have an equation for, and that is kinetic energy. I mean, I've had an equation for work now for a week or two now, but now we've used that definition for work to derive an expression for energy. Energy is this capacity, right, to make changes to your environment. And one of the changes you can make is to, like, throw a ball. You apply a force through a displacement, you do work on the ball, and now that ball has kinetic energy, right? And if it smacks into something, well, it can make changes to it. It can do work to it. So kinetic energy is the amount of work that something can do because it has mass and velocity. Okay, and then using that idea, we also derived the work energy theorem, which said if you're looking at the work done by the net force, it always results in a change in kinetic energy. If the net force acting on an object is doing work, then it will change the kinetic energy of that object. And the work done will be equal to the change in kinetic energy. Oh, one thing here to think about. Kinetic energy, just all by itself, is always positive. Look, it's 1/2 mv squared, right? It's always positive. You can't have negative kinetic energy. But can you have a negative change in kinetic energy? Sure you can. When you catch a baseball, that baseball before you caught it had lots of kinetic energy, right? But then you applied a force in the opposite direction of its motion, of its velocity, and you took away its kinetic energy. You did negative work. You took away its kinetic energy. Therefore, the change in kinetic energy of the ball was negative. That is, its final kinetic energy was less than its initial kinetic energy. So the final kinetic energy is positive, or zero, but it can't be negative. The initial kinetic energy is certainly positive, but when you subtract the two, you can have a negative change in kinetic energy. That's certainly okay. So when you're doing problems with that, consider that. Okay, any questions? Yes?
So, like, work and energy aren't the same thing?
They're measured the same. The question is are work and energy the same thing? Energy is, think of it this way. Energy is this capacity something has to make a change in its environment. Work is when a change is being made in the environment. Work is when energy is in action. It's being transferred. Okay? So, yes, they're measured with the same units. They're measured with joules. Like I would say, oh, I did 20 joules of work. And what you're really saying, is I moved 20 joules of energy from one system into another system. I took it away or I gave it to it. Okay? So they're not the same thing, but they're measured with the same units. basically, yeah, work is when energy is being transferred. Okay, a change in the energy of an object is happening. All right, that's it.